Okay, for this set of problems, we're going to look at the way things were done in the good old days before the advent of electronic calculators. First off, let's explain how to compute the natural log of 10 without using a calculator. One way this can be done is that the natural log of 10 is by definition equal to the integral from 1 to 10 of dx over x. Okay, that's the definition of the logarithmic function. Natural log of x is the antiderivative of 1 over x. So if we look at the picture, we have the 1 over x looks like this from 1 to 10. And so it remains to just simply find the area under the curve. And the area under the curve can be found in multiple ways. A crude way that it can be found is by the trapezoid rule, just kind of breaking this up into parts, and then find the area under each trapezoid. So for example, for this first trapezoid, it would have a trapezoid that looks like this. Then the next part, you have a trapezoid that looks like this. And the areas of the trapezoids added together would be a very good approximation to the area under the curve. Using Simpson's rule would give indeed a better approximation. I can easily imagine that if we lived in the era but without scientific calculators, one way of doing this particular problem would be as follows. This is not necessarily the best way to do it, but this is something that jumps to my mind, that the natural log of 10 is the same thing as the natural log of 8 plus the natural log of 10/8. And so that's equal to 3 times the natural log of 2 plus the natural log of 1.25. And so natural log of 1.25 would again be an area under 1 over x, but it'd be a much smaller area from 1 to 1.25. And then this would be divided into fairly small intervals, and we would use either the Simpson's rule, probably, or the trapezoid rule, probably Simpson's rule, to be able to find the area under the curve. Natural log 2, well, that's going to be the area between 1 and 2. So that means if I find the area between 1.25 and 2, so if I add this area to this area, the combination of those two would be natural log 2. So by doing numerical integration, we can find both of these logarithms to fairly high precision, and we've chosen intervals here that are much thinner than 1 to 10 to allow more accurate evaluation. So by doing something like this, we can evaluate natural log 10 using numerical integration. So let's assume that we've done that, and we have evaluated natural log 10. So we'll assume that the line that I've underlining here, let's assume that that's already been done. If that's been done, let's now calculate the logarithm of 2 base 10 to 9 decimal places. So that's been gotten to 9 decimal places. Let's figure out natural logarithm of 2 base 10 to 9 decimal places. We'll start with the observation here that 2 to the 10th is equal to 1024. And therefore, if you take the logarithm base 10 of both sides, that means that 10 times the logarithm of 2 base 10 is equal to the logarithm of 1024 base 10. Now the logarithm of 1024 is the same thing as the logarithm of 1000 base 10 plus the logarithm of 1.024 base 10, because 1000 times 1.024 is 1024. Okay, so dividing by 10, that means that the logarithm of 2 base 10 is equal to, logarithm of 1000 base 10 is 3. Plus the logarithm of 1.024, more on that in a second, so I'm going to leave some space for that. probably more space than necessary. And then I need to take that and divide by 10. So notice 3/10, we see that the logarithm of 2 base 10 is about 0.3. Now there's going to be some adjustment, and the size of that adjustment we use from calculus. That the logarithm of 1.024 base 10, that is equal to the natural log of 1.024 divided by the natural log of 10. And the natural log of 10 we already know. The natural log of 1.024, let me get rid of the pictures on the right so I have a little bit more space. From the Taylor expansion of logarithm of 1 plus x, that's equal to 0.024 minus 0.024 squared divided by 2 plus 0.024 cubed divided by 3, and so on, alternating minus and plus. And so we'll just basically copy that and put that here in the space that we have here. 0.024 minus 0.024 squared divided by 2 plus 0.024 cubed divided by 3 minus 0.024 to the 4th power divided by 4. And let me just write out a few more terms. Now you may wonder how many places are necessary in order to achieve 9 decimal places of accuracy, and I'll let you figure that out. I believe, just doing this in my head, that if I go out to 0.024 to the 6th divided by 6, let's just see how big that is. So just figuring out this last term we figured out, 0.024 to the 6th divided by 6, that is already 10 to the minus 11th power. So when I go out this far, I should have 9 places of accuracy. And then all this needs to be divided by natural log 10. And so there is an expression for how, without using a calculator, with enough patience, by adding these terms together and multiplying and so on and dividing, we can compute the logarithm of 2 base 10 to 9 decimal places. Finally, for the last part, the natural log 2, that can be computed by, we could integrate again, or we can use the work that we've already got, that the logarithm of 2 base 10 divided by the logarithm of e base 10, and that's the same thing as the logarithm of 2 base 10 times the logarithm of e of 10 base e, or the logarithm of 2 base 10 times the natural log of 10. So that would be the last part on how to compute the natural log of 2. We've got log 2 base 10 multiplied by natural log 10, and that would give you the natural log of 2.